Hi everyone. In this video, I'll be presenting my research paper on 3D object detection using attention augmented networks. As a brief overview, in this work, we use a combination of spatial and channel attention module to both detect as well as regress the 3D bounding box over all the individual objects present in the image. The good part is that our network is end-to-end trainable. We train and test our network on Kitty dataset in terms of average precision as the evaluation metric. Our network is running at greater than 30 frames per second, thus making it work for real-time applications. Going over the network details, we have a special attention module. So here is an input feature map, here is an output feature map. Uh, Here the special attention module is, here H and W denotes the height and the width of the features, and cross and plus denotes the two reshape operators. Similarly, we have a channel attention module. There is an input feature map, there is an output feature map, and in between here, a block C here denotes the dimension along the channel axis, and in between we have like a cross and plus symbol here denotes two kind of reshape operators. Going over the complete network details, like we feed an input image to a backbone which is made up of like rest nets, residual networks. We play in, we play with different kind of backbones like VGG, Inception in the ablation study. We find that the residual networks perform the best. So the feature is propagated to a 2D bounding box detector, followed by a raw line and then a fully connected layer. Similarly, there is a raw line and fully connected layer. Here, delta denotes the deviation of the actual versus the predicted bounding box coordinates. Simultaneously, in parallel, like we have a spatial and channel attention module here. Here, con denotes a convolutional block made up of convolutional layer, pooling layer, batch normalization, and dropouts. So here, plus denotes a fusion operator. So we get a 3D bounding box coordinates here, and using this delta, like the deviation, we are able to get the defined 3D bounding box coordinates. We designed a very own loss functions. But before that, like we present the anchor details for all the three individual anchors like car, pedestrian, and cyclist. Going over the loss functions, here x, z, and y denotes the deviation along the three individual axes. LW denotes the length and the width terms of the bounding box, and these two are the deviation of the azimuthal as well as the complementary to the azimuthal angle. So a complete loss function is made up of first term is made up of like a pos here, and the second is made up of a negative term using these two individual equation. So summing over, like we are able to get the first two individual terms of the loss function, and similarly we are able to get the third using the bounding box coordinate values along all the three individual dimensions. So the complete loss function can be written as this, where alpha, beta, and gamma are some parameter values which we have fixed here. Going over the evaluation metrics, like we use average precision as the evaluation metric. We present the implementation details. So going over the results, like our network uh, performs better than most of the previous state of the art across a range of like evaluation metrics. Our network is performing the best, uh, especially on the easy and the medium part, although it is not uh, the state of art on the hard. So that is something which is lacking, but still it achieves like a good enough trade-off between the the frame per second as well as the average precision. So this was the quantitative results for the car on kitty validation set. Similarly, like we have the performance on car on kitty validation set. Like we compare using different easy, medium, and hard parameter values for intersection or union metric. In this curve, we present the precision versus recall curve for 3D bounding box detection for each of the three individual car, pedestrian, as well as cyclist. In this figure, we show the predicted 3D bounding box coordinates, which is shown in orange here, while the ground truth are shown in blue here. We present the ablation study using different backbone networks and find that residual networks perform the best. It was consistent. The results were consistent across all the three individual categories. We played with attention modules here and find out that the best results was achieved using a combination of special and attention module across again the individual easy, moderate, and hard evaluation metric for average precision. We also played with adding the loss function terms and find out that the combination of all these three individual loss functions perform the best in terms of average precision as the evaluation metric. So as a brief summary, like in this work, we propose a novel network for 3D bounding box detection, uh, or maybe 3D object detection. Uh, the good part is that our network runs at good enough FPS, thus making it work for real-time applications. So here we use a combination of spatial and channel attention modules to achieve results on par with the state-of-art uh, networks. We train and tested our network on Kitty dataset, and uh, and we demonstrate that our network uh, performs good enough using a range of evaluation metrics. In the future, we would like to extend this work and maybe add other kinds of attention mechanism or play around with different attention mechanism to make more lightweight network. Although this network is running at good enough FPS, but still it is demanding. So that is something which we would like to extend it further. Maybe remove the backbone, uh, which is which is residual network in this case. So yeah, thank you for listening.